How are you guys feeling?
Pretty good. We're relieved that the tool's there.
Yeah, we're almost there. That's right. Um, so just a little update here. I had to do some revisions on this, so I don't know if there's 41 points or 48 points still available. It'd be close because there's some questions I had to remove from because we didn't do those last two sections that we were planning on doing. Right, so that changed a little bit, but like whatever. What's a point or two difference one way or the other matter? I don't know that it does. But I replaced the questions with something else, and I don't remember how many points the old question was when after I deleted it, and I guessed this, so I didn't worry about the total points. So that might have fluctuated just a touch. Let's talk about a little bit on preparation, like what you should expect or what you should try to do. For part one, you'll want to know your theorems, facts, and definitions. And you'll want to understand what these mean in like multiple modes. So symbolically, what does this say? Graphically, what would this say? Tabular, like in a table, what would this look like? Etc. And that's really just so you can generate a counterexample, kind of wherever you feel most comfortable, right? Additionally, you'll want to know your derivative shortcuts and be able to use them abstractly. Like if you want to do the derivative of f of 2x times g of x to the negative 1, like you're using like chain and product and quotient, like the rules like that, but it's abstract because we don't tell you what f and g are. You just have to kind of like, so like specifically things that you'd want to make sure you intermediate value theorem, extreme value theorem, mean value theorem, squeeze theorem, first and second derivative test, the absolute minimum maximum test, Rolle's theorem, continuity of point, differentiability, limit definition of a derivative, differentiability implies continuity, definition or limit definition for asymptotes, limit definition for their different type of discontinuities. Oops. It's probably discontinuities. So for part two, those are like the regular problems. So examples of things that you might be asked to do, like evaluate a limit or compute a derivative, and you might have to combine multiple chain product quotient rule for something like that. You should be able to compute a derivative from an implicit formula like x plus 2y minus xy equals 0. You should be able to write an equation of a line tangent to a curve at a given point. Solve a related rate story problem. We're just asking you to do like find the the rate in which volume is changing with time or something. We're just asking for like one thing. Yeah.
So for related rate story problem, for some of these things, is it gonna be included in every question, or can we like skip over something that we're like, I'm not that confident about, I'm more confident on this
Again, there's like regular question, 41 total points, you need to acquire 15 of them. So like however you do that, it doesn't matter.
Okay.
That's your goal. So will you do every problem on the test?
No.
No. Should you try to do every problem on the test?
No.
No, you run out of time and end up like a whole section blank because you did 25 true and falses and then like 6 of the next questions and then you ran out of time. It's like, oh boy, I budgeted my time really poorly there. You might have a proofish problem where you ask you to like prove that some equation has a solution on a given interval. Might ask you to find critical numbers for a function or determine the absolute min and max for a function on some closed interval. And then part 3, again, you want to look over some of the FRQs we've done, but the topics there'd be kind of centered around continuity and differentiability, specifically probably in a piecewise function, related rates, optimization, minimum, maximum of a function, increasing, decreasing, concave, up, down, inflection points for a function. So those are kind of the areas in which these FRQs will kind of be drawn, or the topics will be drawn from. All of the point values for questions in part two through parts 2 and 3 should be labeled on the problem. It'll tell you like, oh, there's a 1 point, there's a 2 point, there's a 4 point. It'll be listed there for you, so you can have an idea of like what you're kind of accumulating as you go. Format questions or anything here, Chanel?
So if a question has like parts A, B, and C, for instance, can we solve like parts A and B of one
Yep.
question?
Yep. Anything that's a part, you can do parts of, and you get partial credits. In fact, you do like 10 problems and get 1 point out of 4 for 10 of them, and that's 10 points still, right? So like, it's okay. So again, like trying to make this as easy on you guys as you can skip around, do the stuff you feel good about, and concentrate on the stuff that you understand and you're good at. So does this help clarify kind of like what you'd want to be, or where you'd want to be kind of focusing on? Yeah, Chanel?
So for the increase and decreasing, like that last bullet point, is that like draw a function based on that stuff? Or is it just you're finding it?
Probably just finding it.
Okay.
Christian?
The original like derivative definition we got of the f of x plus a over x plus a, do we even need to know that, or just
Well, probably for true and false, it would be handy, potentially, since it's one of our major definitions. And that's only one version, right? You forgot the limit as x approaches a, part of that. The other version is the limit as h approaches 0 of f of x plus h minus f of x over h. That's the other version of that definition. And again, like fair game, that was like a legitimate homework question that we could ask you to use the definition of a derivative to show that like the derivative of this thing is this. Like should be able to manipulate a limit to get that to happen. But again, like you have a lot of flexibility. If you don't feel good about that kind of problem, you can always skip it, right? Work on something else. Chanel?
So do you think that like the textbook problems, the MCQ, and the FRQ are like the best study sources for the final exam? Like, because that's like what we usually study for like previous tests.
Yeah, I would think about like, okay, what was the major stuff that we did, right? Like, what were the major skills? And like, make sure I can kind of do that, and I should be okay. I wouldn't worry so much as like, oh, I got to practice like this one problem, as in like, I want to just be like, okay, if I need to find a maximum or minimum, what are the different ways I can do that? How do I select which way would be the best way to do that? You know what I'm saying? Like, I would think about it, especially come final exam time. My goal with studying for a final exam, especially for mathematics, is to like recategorize like what have we done this semester, and like build a file cabinet of my knowledge so that things are organized and connected, and I can, like regardless of kind of the presentation, it's like, okay, well, this is a weird presentation because I'm given a table of values instead of like an equation, but it's still just like it's asking me to do this. I'm just going to have to use the table to do this. Kind of, you know what I'm saying? That's the way I would start, is by like, okay, I'm going to like outline like the major skills and kind of like, like what are the problems ask me to do? Like, what is the goals? And then like, what are the techniques I use to do those things? And when do I know like when to select which thing? And then I would do some practice. And sure, I think the textbook problems and the, like the old test questions and the FRQs are good sources to kind of do some practice. But before I wouldn't limit myself to practice. I'd spend a little bit of time just kind of like outlining like the major things that I've done and like how do I do those major things, so that I have a little bit of a, like a reorganization of this stuff in my head. Does that make any kind of sense?
Yeah, are old test questions like really good, or is it like,
Some of them probably are. Am I being a little bit cagey here because I want you to do a lot of stuff? Yes. But if you knew it for the test and you felt pretty good on the tests, should have no problem in accumulating the number of points that you need to do well here. Even if it's I knew the test I got, the questions I knew how to do, I knew, and I got full marks on those, and the questions I didn't know how to do, I really struggled to get a lot from those. Should be able to do fine on the exam, because you can do, you don't have to do a lot of the questions available to get your marks, and you can pick the stuff you feel good about to some extent, right? There's a lot of choice that you have available to you. Again, my recommendation would be I would just go through and do, if I know how to do it right away, I would do it immediately, with kind of keeping a tally of how many points I feel like I have accumulated. And then I'd move on. I'd stop once I got to okay, I think I did 15 points here. I'm stopping, going to the next section. And I'm going to go through try to accumulate at least 10, 15 before I do any backups, right? So I'm going to go through and do everything that I know how to do right away until I think I have, the necessary points for that section, and then move on. And I'm not going to read every question if I don't have to. I have no intentions of doing every question. My goal is to just accumulate my points. And if I get, if I go through and it's okay, I think I did 10, 15, let me do some backups, then I'll do some backups as time permits, and start in the section I feel, the worst about, and do some backups there. The nice part is with the free response and the part 2 and part 3 questions is 1 4-point backup problem can cover a lot of mistakes, right? You can do 1 problem in there, and it's okay, I have I've done 20 points in this section. I think I'm probably good. I felt pretty good about all 20 points worth of problems. You know what I'm saying? That's the way I would approach this. So yeah, I mean, I give you some ideas of the types of problems you should do or should be able to do. I'd go, okay, limit problem. What am I going to use to do a limit? At this point, I would say there's probably 3 techniques at most that I'd worry about. They would be, I would not think about that. Direct substitution would be the first thing I would try, right? L'Hopital, if the direct substitution gives me something indeterminate. The third thing is the squeeze theorem, because what if I'm given an inequality of, I'm just told the limit of f of x, and I'm told f of x is bigger than this and smaller than that. Those would be the 3 things I'd worry about. It's okay, I need to do, be able to do a limit these 3 ways. And the details can be a little different, could be tricky because of the details, but if I know what to do, I'd feel pretty good there, right? Computer derivative. Well, okay, that boils down to, I gotta know all my shortcuts. I gotta know chain quotient and product property. And then it's okay, now I just have to do some practice, right? Make sure that I know, when do I start with a chain rule versus a product rule versus a quotient rule? How do I do those in the right order? Make sure I don't miss any chain rules. When I have cosine of 2x, I don't forget that there's a chain rule in there. But there's a trillion variations of problems inside of that. But if I know the derivative rules and I feel good about applying them in the correct sequence, it shouldn't matter. It could get nasty, but I can work through nasty because Mr. Kulik doesn't need me to simplify down to simplest form. He just needs me to do the calculus. If I want to compute a derivative from an implicit formula, again, like just kind of all the same. I just have to make sure that I don't miss, like a product rule or quotient rule or a chain rule or something. Like I have to remember my dy dx's when I differentiate my y's, but they're kind of all the same. And sometimes the algebra is yucky, separating the dy dx or whatever, but like I know that I can do the calculus part at minimum, and I know what to do. Maybe the algebra gets a little hairy in there. Maybe it doesn't. Maybe it's pretty straightforward. But they're all kind of the same, right? Like that's the way I would be going through and doing this. Like write the equation of a line tangent to a curve at a given point. Well, y minus y1 equals m times x minus x1. The x1, y1 is going to come from f. The m is going to come from the derivative of f. And just do the derivative and plug things into the right places and plug it into the formula, right? Like that's the way that I would approach this. It's just like I'm going to go through these question types, kind of think about what I need to do, like what are the steps, and then if I do some examples to kind of like reinforce the steps. But that's the way I would approach like a mathematics final. I'm going to bank on the details I kind of know throughout the semester. I just need to like really nail down the procedure, like what are the steps to do the problem, and the little nitty-gritty details. I'm going to bank on like my previous algebra skills and my previous, like the calculus details that we've really focused on throughout the year, kind of carrying me through there. And I can always work on those details if I'm like, yeah, I'm a little sketch on the details for this kind of problem. I'll do some examples to work on my details. But like more what I'm going to be worried about is like, what is the procedure for this kind of problem? What are the steps that I need to do? Because when I'm assigning partial credit, that's kind of what I'm looking for. Like if to do this kind of problem, you need, to do these three things and then put it together. Well, guess what the 4 points for the problem would be? Be like this thing, that thing, and then putting it together. So if you can, like even if you make some mistake in the details, if you accomplish like 2 or 3 of those things, still a lot of partial credit for that problem. Chanel?
What's an example of a proofish problem? Like what does that mean?
So we did these way back when we did like the intermediate value theorem in chapter 2, and then we saw these again in like the mean value theorem section in chapter 4. So like, like we did something like this. So it's harder when it says exactly 1. It's easier if it just has a solution. If it has a solution, all you need is that part, right? You have a continuous function. We know that, if I use, the function can be negative, it can be positive. So somewhere in that interval, it has to pass 0 because of the intermediate value theorem. Done. So
it could be something like one railroad, but it's likely going to be like something continuous, like intermediate value theorem stuff.
Well, if it's just like, like has a real root, then it's just intermediate value theorem. If it's exactly 1, then you need like first to show it has at least 1, and then you do a contradiction. You make this Rolle's theorem argument to generate a contradiction. But that's kind of the way that I would be approaching, thinking about this kind of a problem. Is like, okay, step 1, it's like, okay, I need to use the intermediate value theorem to show that, like this has at least 1 solution. What do I need to do to show the intermediate value theorem? Well, I need continuity. That's easy to show, but I do have to remember to say it. And then 2, I need to find, like some value of x that evaluates to a negative and some value of x that evaluates to a positive. And then the intermediate value theorem says, okay, in between those 2 x's that you use, there has to be some x that makes the function 0. That's at least 1 solution. And then to get the contradiction, I say, okay, assume that there's another. So I have like, 2 things that equal 0, because of Rolle's theorem, I know that there's somewhere in between where I have a derivative of 0, and then I take the derivative and show that I can't actually, there's no solution in that interval, or maybe no solution at all. And that's my contradiction. Giselle?
Can we just like go through the IVT, EVT, and VT? I don't know. I just like
Yep.
don't understand that.
Sure. Oh, I want it here. Okay. All right. So the IVT. So for the hypothesis, we need continuous on a closed interval. And we need to be able to say that there's some yeah, I think that's just supposed to be that. And your conclusion then says there exists a C on that interval such that f of C equals K. So graphically, what is this saying? So let's say this is the line y equals K. Here's some point A comma f of A. And here's some point B comma f of B. If they're continuous somewhere along the line, we have to cross that line y equals K. So there has to be some value of x that gives you K as an output for our function. Right? That's kind of what it's saying. Does that make sense?
Yeah.
And I think the picture helps me more than anything else, right?
Mhm.
It's just like, okay, so if I have, point down here and then a point up here, somewhere in between them, they cross every y value in between them, right? The function does.
So to like have this work, it needs to be continuous and on a closed interval and what else?
And then you need to have some, some value of the function below your desired value and then some value above it. You just need like a y coordinate that's less than the value you're looking for and a y coordinate bigger than the value you're looking for. And then somewhere in between there has to be an x that gives you that y value you're looking for. Katie.
What's like the biggest thing that shows you that use this? When you know that you have used this?
So this is for, like, it's just showing existence. That the function can have some value. So if I need to show that the function can equal 0, like I'm solving an equation, or just if like, can f of x equal 12? Well, then I just need to find an x that when I plug in I get something less than 12 and find an x where I plug in and get something bigger than 12. And then as long as it's continuous, in between those two values, I'm going to have some x that gives me 12. You know what I'm saying? So the extreme value theorem says that we have to be continuous on a closed interval. And the conclusion is then that on that closed interval, somewhere f has to have an absolute maximum and somewhere it has to have an absolute minimum. You know, so like if it's just something dumb like that, there's my absolute minimum, there's my absolute maximum, right? But it could be something like this, where like, okay, my absolute maximum would be here, my absolute minimum would be there. You know, or it could be something like this, where really every point on there is an absolute max and absolute min. But like, that's what it's saying. Does that make sense, Katie? Giselle, you okay?
Yeah.
All right.
And then you just use that if you need to find.
No, it doesn't find anything. It just shows that it exists. All it does is give you existence.
So it's asking if there's an absolute maximum.
Correct. Notice that it doesn't guarantee that the derivative is 0. Because you could have had, you know, we could have this situation where the derivative is never 0 between A and B, but we have an absolute max and an absolute min because they're at the endpoints.
So what is that?
Yeah, all it's doing is showing existence. So it doesn't, most of these value theorems don't actually give you anything. They don't produce anything. They just show that it's possible to do this. That this thing, like this property has to be there. How do you find it? I don't know. Well, I know it has to be there.
So like on the part where we like prove this and stuff, like what kind of like question, like I mean, I guess like we could look back.
So like if I did this, I say like if f is continuous on AB, and I'd say then
So it'll be like that direct.
it could be something like this. Now, what would you say here?
False.
You should say false. And one way you could say it is because, well, if it was closed intervals, this would be true because it's the intermediate or the extreme value theorem. You could say that. Or you could be like, well, you could have like a picture, like here's A and B. There's an f that's continuous on A and B, but it has no absolute minimum, right? Like you could draw a picture like that that's like, you know, and just write like no absolute minimum.
It could be as simple as just saying, okay, it needs to be a closed interval for the EBT.
Yeah, yeah, you can state like how you know it's false, right? Like whether it's, okay, here's a picture that like meets the conditions but fails the conclusion. Or you can say like, okay, I see what you're doing here. This looks like the EVT, but it's missing this criteria. Like if it had this criteria, then it would be true. You know, like you can tell me what you need to change to make it true. That would be okay. Particularly if it's something like that, where it's like, I'm just really checking to see that you know the extreme value theorem. Like
What
it's
would be
usually pretty
something-
obvious.
What would be like something more like complex that you would say? 'Cause this is like really basic. It's just like the difference of the closed or open interval.
Well, I think that's actually pretty, like, I don't think that's basic.
Oh,
I think
okay.
I think that's pretty tricky
Okay.
because it looks a lot like the extreme value theorem. But if you don't understand like why that closedness is important, like what could I make, what kind of function could I have with that makes this fail without it, right? It's really hard to draw a counterexample if you're not like, oh, see, if I have an open interval there, then I can have like an asymptotic behavior,
Right.
and that's going to kill off either, you know, potentially both of them. I mean, like, you know, you could have something like this that has no absolute mins or no absolute maxes, right? Like, so I don't think that's a trivial or basic problem at all. I think that's very similar to like what the things might look like.
Got it.
You know, it might be something like, I just have a definition that's, you know, like not quite right. And it's like, okay, well, that's not the, you know,
Yeah.
or I could have just like, you know, like what's the definition of continuity at a point? Do you remember this?
At of the two limits are the same and the value of the
Yeah. So what Nolan's saying is that if this is true, then we have continuity at a point, right? And it's also equal to the function, right? So I might say, like, if f is continuous, then, I might say that. And what would you say to this? True, great. And your explanation could be something like, since f is continuous, it's continuous at C, done, right? Maybe I'd say, it will be specific instead of watch my personal pronoun usage. It's maybe not obvious what it was. So yeah, I just say since f is continuous, then f is continuous at C, and that's the definition of continuity, right?
Like you just do the MBT, and this is like really helping.
Yeah. Let's see.
Can you also do Rolle's theorem?
Yup. So the mean value theorem says if f is continuous and differentiable, we gotta be careful here, because it's continuous on a closed and then differentiable on the open, then there exists a C on that interval such that f prime of C equals the average value of f. So this is like the hypothesis. And then this is like the conclusion. So notice here you need continuity and differentiability, right? And what that does is it just guarantees you there's some place on the derivative that's equal to the average of those two. So like if we have a picture, let's say this is A comma f of A, and this is like B comma f of B, and like here's my function, that's continuous and differentiable, right? I can tell it's continuous because it's smooth, like it's a unbroken line, right? And it's differentiable because there's no sharp corners. So like this line is the value where right? So I'm just saying, okay, where is the derivative, or where can I draw a tangent line to the curve with the same slope as that line? Well, like, could do it here, could do it here, And no matter how I draw, like, that curve, as long as it's something that's continuous and differentiable, I'll always be able to find some tangent that's parallel to that secant. The red line is a secant line because it's like an average value line. Is that?
Yeah, this helps understand.
Yeah. So like if I miss the differentiability piece, right? So say we have like, if I try to draw something that's continuous but not differentiable, I could do this, right? So there's my secant there in red. Where can I draw a tangent that has the same slope as that secant?
You can't
I can't because I lost the differentiability piece, right? Like, that's why I need the differentiability, because if I didn't have that, I could have something like this with a sharp corner, and well, there's this, the derivative only has two slopes. The slope is, whatever this is, and then it's whatever that is, and there's nothing in between, right?
So it's false with a sharp corner, jump, discontinuity.
Yeah, so like, again, we need continuity and differentiability. So the graph would have to be continuous all the way, and it can't have any sharp corners. So it can't have any open circles, it can't have a removable, it can't have an asymptote, it can't have a jump. And I think like this kind of like, what would the picture look like? This is how I conceptualize most of these theorems. I think about like, okay, what is this really saying? And it's like, it's telling you, if you can draw a picture like this, then this other thing has to happen. This picture also has this feature. And I think that's oftentimes the most helpful way to think about this stuff is like, I like pictures. I'm a picture person. I think it really helps your intuition, getting away from just the words and the symbols. I think that helps me anyways, and I think it builds like a nice conceptual foundation for kind of what's happening. So I think that this is really like lovely time spent, like thinking about these things really conceptually without numbers and values and just like graphs. You know what I mean? Yeah, of course. Do you guys want to talk a little bit about some of the optimization homework? We haven't talked about any of that yet. Yes, Chanel.
Oh, I was just wondering if you could do Rolle's theorem. I'm so
Oh,
sorry.
sure. I just have to double check if it was open or closed. Okay. Got it. So it says that if f is continuous on the closed interval AB, differentiable on the open interval AB, and then f of A equals f of B. So that means that like they're the same height, the 2 points are. If I try to draw this with smooth curve and connect them, somewhere along the line, I have to have a place where the derivative goes to 0, right? I have to have some maximum or some minimum, or I could have multiples, right? Like I've drawn here. You could have just one, right? But if you lose the differentiability, well, I can do this. Now there's no place where the derivative is 0. If I lose the continuity, you could have like this. Again, no place where the derivative is 0. Or if they were not the same height, if I had this, again, I can draw something where there's no place where the derivative is 0. Yeah, so they have to be the same height, and then to connect them, somehow, if the curve is also continuous and differentiable, somehow I have to make a maximum or a minimum or lots of them along the way. Places where the derivative is 0, because it has to be a smooth curve. So I'm going to get the differentiability the whole way through. So that means no sharp corner, so I'm going to get some kind of maximum or minimum somewhere along the line where the derivative is 0.
So it could be like this, but as long as the 2 points are like horizontal to each other.
Yeah, they have to be at the same height, and then you could have like, like lots of places where the derivative is 0. But all Rolle's theorem says it has to happen at least once. There has to be some C on there. Could there be lots of C's? Sure. So again, yeah, this would be existence of a max or a min for sure. You could use this. Again, it's another existence theorem. It's just saying, okay, we got to have some critical values in here. Some places where the derivative is 0. Does that feel good?
Yeah.
Okay. And again, I think like drawing the pictures of like what is, like what does this part of the hypothesis guarantee? Like why does that have to be there? If I lose that, what kind of picture could I draw to make this not work? I think that's really helpful. Chanel?
So is it just, I just want to like recap. So is it just pretty much saying that if the function is continuous and differentiable, then there's going to be at least like one max and min that's, or if it's f of a.
You have to have two points that are the same height.
The same height. Okay.
Yeah, somewhere in between those 2 points, there's a place where the derivative is 0.
Okay, got it. Thank you.
So there's like a max or a min in there somewhere. At least a local, right? Because we can't even draw, like, even if I did something like that, well, there's still got to be, still got to be a local, even though we have another spot where we're.
Well, what about absolute?
Can't say anything about absolute.
Okay.
This will say nothing about absolute. Now that place where the derivative is 0, could it be an absolute min or a max? Sure, but this doesn't give me enough information to say that at all.
Okay.
Because who knows what's happening before A or after B, or what else is happening in between them, right? There could be lots of C's in there. And the one that you find, if you did go ahead and find one, may not be the only one in there, and that doesn't tell you beans all about whether it's an absolute. You have to have all the critical values to say it's an absolute. You know what I mean? And in fact, it was, where was that? It was here. This was our theorem for if you have looking for absolute extrema on an open interval. If you have, some C, and everywhere before that C is increasing, and everywhere after that C is decreasing, well, then that has to be an absolute maximum. And if you have the reverse, everywhere before the C is decreasing, and everywhere after the C is increasing, well, that C has to be an absolute minimum. But that can only happen if that C is your only critical value. That has to be your only critical value. And you have to have before that, like everything is increasing or decreasing. If you have some other critical value, even if it's not a max or min in between, can't say that because, well, it's not increasing everywhere if there's a place where the derivative is 0. You know what I mean? So if you're able to show that, okay, Rolle's theorem says there's at least one C there, and I can show that it's actually the only C, and, the derivative is always positive or negative on one side and always the opposite on the other side of that C, then I can say it's absolute, but it's a much bigger bar to clear. Is everybody okay there? So a lot of these true and false will be based on one of these theorems or rules or definitions with just possibly a little tweak a little piece missing or a piece changed that would make it false. Chanel.
I have two questions. So for 4.5, will we on the test have to like sketch a curve?
Feels like too much.
Two.
That would be like a million things you have to do. It'd be like 20 minutes for that one problem. Feels like too much task.
So there's nothing on 4.5 on the test?
I would ask you to do parts of things, but I would never ask you to do the whole thing because
Okay,
there's
so, like-
too much to find,
Okay.
right? Like you gotta find the intercepts, you gotta find the increasing, decreasing, you gotta find concave up and down, and the inflection points, and the mins and maxes, and just like, and the asymptotes, and the domain, and just like, it's like there's just so much stuff to do on that, and then you have to sketch a reasonable curve out of that. That's like, it's too much time to do all that thing.
Okay.
Would I ask you to do one of those individual parts?
Yeah.
Absolutely. But to do the whole thing in context, like where one thing screws up everything else, it feels like a bad exam question because so much of it is like, if one thing goes wrong, it kind of all goes wrong. Katie.
When do you use the RBT? Isn't that what it's twice differential?
Oh, yes. Was it twice? Did I say twice or not twice? That's a good question. No. You do not need twice differentiable. One differentiable is enough.
So like in the prompt, it just says like after differential, continuous, then you can use that.
If it said it was twice differentiable, you could still use it. Or thrice differentiable, right? Like if it's twice differentiable, it means it's differentiable, and then its derivative is differentiable. Like that's fine. That's enough. And then it's more than enough. You get what I'm saying? Oops, I didn't mean to do that. Shell, what's up?
Come back to me.
That's okay. Should we do some optimization problems, some 4-7 stuff? I had a couple that I thought were good ones that I had picked out. Is that okay if I just pick?
As in like this is similar to what's going to be on the test.
Maybe. Or at least like a similar level of difficulty.
That's good because I was looking at them and I was like, which ones are?
Let's see. So this is like 29, 30, 31. Actually, 31 I think was the algebra gets too terrible there. Although like the problem itself is fine. The actual algebra at the end is like just ridiculous. So let's look at 29. So it says a right circular cylinder is inscribed in a sphere of radius r. Find the largest possible volume of such a cylinder. So picture what's going on. So we have a sphere, and inside that sphere we have a cylinder, right? And inscribed means that like the cylinder's like all four corners of the cylinder are touching the sphere, right? And because it's a right cylinder, like the center of the cylinder is at the center of the sphere as well, right? Everybody's okay there? So it's asking about the volume of the cylinder. Well, I know the volume of the cylinder is pi r radius for the cylinder squared times the height for the cylinder, right? It's too many variables in there. I have two variables, right? Both the radius and the height would be changing as I change the dimension, as I try to fit a different cylinder in there. Whether I have like one that's wide and short or one that's tall and skinny. Everybody agree? So what I want to find straight away is a way to resolve this so I can write either RC in terms of HC or HC in terms of RC or something. So what I'm going to do here is I'm going to draw a picture. So I can see here that from the picture I've drawn, the height of my cylinder should be 2x. And then I can say that RC squared plus x squared is equal to RS squared. Is everybody okay? So what I'm going to do is I'm going to solve my equation in terms of, or I'm going to rewrite my equation in terms of x's. Why does it matter that RS is in there? Why am I not concerned about that being a second variable? RS is a dimension for the sphere, which is constant. The cylinder is what we're changing to fit inside of the sphere. The sphere is fixed. That thing's not moving. That's just a sphere. The cylinder that's inside of it, we're either going to make like short and wide or tall and skinny or something kind of in the middle. That's fitting inside of the sphere. The sphere is fixed. So I've accomplished what I wanted to do. I've got this down into one variable. What's the domain for this function going to be? What are the possible values of x? It's a dimension, right? So the smallest it could possibly be is 0, but it can't actually be 0 because if I had 0 height, it would just be like a circle. That's not a cylinder. So it can be an open interval. And the biggest that x could possibly be is the radius of the sphere, right? So look at our picture here, right? The tallest that could be is if it's just the radius of the sphere, in which case you have a straight line as your cylinder, but that's not a cylinder, so we can't include RS. That's my interval. Is everybody okay there? So I have my equation, I have my domain. What I need to do is differentiate this, because I need to look at where the first derivative is equal to 0 to find my critical values. If I want to find a max or min for volume, that's like finding the max or min for our function. So if I'm looking at this right now, this looks like I'd have to use a product property on it to differentiate it. Nuts to that, I'm just going to do some distributing and then don't have to use a product property because, well, I'd rather do a little bit of algebra and not have to monkey around with like hard calculus. Everybody okay with how I distributed? So do my derivative. So there's my derivative. What type of function is that derivative? Polynomial, yep. So the domain for polynomial is?
All real numbers.
All real numbers. That means that whatever the domain for f, which was also a polynomial, should just be the same as the domain for f prime, right? Easy to see that, like, doesn't matter what I plug in for x, I don't get something undefined. So I can pull anything from the domain of f, and it still should be in the domain of f prime. Okay? So now we'll set it equal to 0. So what am I solving for again? What is the variable here? x. So subtract the 2 pi r squared from both sides, and then divide by 6 pi, or negative 6 pi, I should say. And then we'll square root both sides. Actually, I'm going to write it this way. So far, so good. Now I can discard one of these two solutions immediately because it's not inside the domain of f. Which one can I discard? The negative. So now I just need to find, is this a max or min? How would you suggest I do that? We have an open interval. So I would need to use either a first or second derivative test, correct? I would use the second derivative test, absolutely. Why would I do that? The derivative's going to be pretty easy because all I'm doing is differentiating this. What's the derivative of 2 pi rs squared? What is it, Christian? 0, because it's all constants. And the right, because the rs is a constant. It's dimension for the sphere. The other two things are just numbers, so it's all constants. And the other piece is easy. Again, the variable in question is x. And I notice that this is less than 0 if x is greater than 0, which it is. So what's that tell me? It's a local maximum. And because our function is concave down everywhere, it's actually oops, I meant for double prime there. It's our absolute maximum. Now the question asked for the volume. So now that I have this, I'm going to go back and plug that into my volume formula. Where was that at? Here. And now I'm just going to do some cleanup. So I'll make a common denominator here. So what do I get? 4 pi rs cubed over 3 root 3, I don't know, units cubed or something. I don't think I gave a unit in this problem. But that's the idea, right? So the first step, draw yourself a picture, come up with the equation that you need. You may have to take that equation, rewrite it so that it's single variabled. Maybe before we even do that, identify constants versus variables, right? Like identifying that rs was a constant was important. Once you have your equation in a single variable, take the derivative, set it equal to 0, find the critical values, identify which critical value is the one you're looking for. the relevant min or max, and then plug it back into your original function to find the actual value. That was basically the rundown there. The one that the ones I put for you on the test, I probably give you the picture. It's probably a multi-part one, at least the one in the free response. Like, I tell you, like, okay, here's the picture. Like, here's some labels. Like, write down the labels for everything else. Like, I help you along the way to, like, get the equation. So it's not so bad. Makes it still doable after you have it. Yes?
Could you give us that little triangle that you drew in?
I'd probably give you what you needed. It might not, I don't have it's not a cylinder and a sphere. I'll tell you that. It's a different shape and a different shape. But the picture you need, I include. So I include everything you need in the picture to come up with what you need. You know what I'm saying? I think you'll be happy with what you got. Or again, if you're not, then try not to do it, right? Like, try to find stuff you know how to do on the other parts. That's okay. Do you want to do another one of these? Yay or nay? Yay? I'll do a yay. 30 I didn't assign as homework, but I think it's probably a good one. So right circular cylinder is inscribed in a cone with height h and radius r. Find the largest possible volume of the cylinder. So there's my cone. And there's like my cylinder, right? All right, so what can we label here? AC is the radius of the cone, and that's a constant. EC is the height for the cone, that's a constant. BC is the radius for the cylinder, and that's a variable. DC is the height for the cylinder, and that's a variable. So the volume for my cylinder is, again, pi r squared height How am I going to resolve that into a single variable, though? Similar triangles, yeah. So I can say that like ED over like BCDE, call that F, DF equals EC over AC. So filling some of this in, so DF is the radius for the cylinder, AC is the radius for the cone, EC is the radius for the cone. What am I going to call ED though? It's the height of the cone minus the height of the cylinder. Now, to me, it looks a little bit more appetizing to try to get the radius for the cylinder by itself. You guys agree with that? That seems more appealing than trying to separate the height of the cylinder. Oops. That's supposed to be height. And now I can start substituting, right? Yeah.
They go to the bathroom.
Yeah. And again, I'm going to kind of distribute things through here. Let's do it maybe a piece at a time. So I'll do that, right? That stuff was constant, so I'm just going to pull it out to the front. And then I can distribute the rest of that stuff through. Now if I differentiate, I feel like I could have done a little better job with my naming, huh? This is pretty annoying. Yes, Katie? Oh no. Yeah. That was supposed to be squared, huh? That's okay. Squared. Thank you. There we go. All right. Well, that just looks like I'm stuck I could FOIL that out, or I'm just going to product rule and chain rule it. It feels like 6 of one, half dozen of the other to me now. So set that equal to 0. This piece is a constant, right? So I can just divide it out of there. What did I do? Did something bad here. I have to go back and look now. Let's simplify this a little bit. I don't like what's going on. So I'm just going to call ECH, ACR, and then I'm going to call this spot Y. I'm going to call that X. So I have that X is equal to Y R over H. So the volume is pi Y R over H squared times H minus Y. Or do I want to do it the other way? I don't think it should matter. Okay. That's better though. So the volume is R squared pi H squared, and then I'll distribute the Y squared through H squared minus Y cubed. Yeah, that's looking better. So that's going to be R squared pi Y squared over H minus R squared pi R squared Y cubed over H squared. Then if I do my derivative, that's going to be 2 pi R squared Y over H minus 3 pi R squared over Y squared over H squared, and set that equal to 0. Yeah, go ahead. You're welcome. Yeah, that's looking better. There you go. That looks better. Obviously, this has to go, right? Remember, y is the gap between the top of the cylinder and the point of the cone. If that's 0, then your cylinder is just a straight line up and down. That can't be possible. After this, you just do your second derivative test and then plug that back into the volume. I'm going to stop here because it appears that we're out of time because I see people backing up. But that was the gist of that. Again, procedurally, kind of the same thing. Notice that like halfway through I got frustrated with my notation with the cones and cylinders on the R's and S's. It was just getting confusing. So I just went back and like, I'm going to call this X and Y and then R and H just for like simplify my life here because I started getting confused with the notation and it felt like things weren't going the way I think I screwed something up. And boy, it's a heck of a lot easier without like a ton of subscripts on there. Yes, Chanel.
Would you say that their optimization problems are like easier than later?
It depends on how comfortable you are with like the first and second derivative tests
Oh, okay.
and like how comfortable you are visualizing the situation. Just kind of depends. I mean, they're very similar, I think, in a lot of regards. Like implicit differentiation as to related rates, what like min-max first derivative, second derivative tests are to optimization. It's kind of like, they're like just like the natural application follow through for these two topics. Katie?
What would you use like the EDT versus like Rolle's theorem? I feel like
They're really cool.
So the difference is the Rolle's theorem, the endpoints of your interval have to have the same height. EVT, they do not.
What makes the
Well, here's the thing. If you have the conditions for Rolle's theorem, you have the conditions for the EVT, right? If you have the conditions for the EVT, you do not have the conditions for Rolle's theorem. Rolle's theorem requires that extra piece where the endpoints of your interval are the same height. And that's the key difference. If they're the same height, then they can't be a min or a max unless it's just a flat line, right? Does that help?
Yeah.
Okay. Chanel?
So you would say that these two columns are like a good reflection?
I think this is the same level of difficulty that I would expect for the optimization problems that you might see on the file.
Okay, got it. All right, thank you.
I think they're the same level of complexity. I think they're the same level of, like any trick in here would be the same kind of trick you'd use on that, on that one.
Focusing on these problems or the minor.
I think that's fair representation.
Okay.
Sure.
Thank you.
You're welcome.